Okay, picture a massive transmission tower for a second. Ever wonder why the whole interconnected system doesn't just, collapse? Welcome to this explainer. Today, we're diving straight into the absolute puzzle that is keeping our massive electrical grids perfectly balanced and stable.
Here is how we're breaking it down today. 1. The grid's balancing act. 2. The 4 key variables. 3. Load buses, or PQ. 4. Generator buses, or PV. 5. The swing bus. And finally, 6. Solving the power flow.
So, this is the million-dollar high-stakes question, right? How do operators actually know the grid won't just black out in the next hour? Well, it's all about perfect equilibrium. Under steady-state conditions, generation absolutely must match consumer demand plus all the system losses. If you overload a line or lose that delicate balance, the system fails. No pressure, right?
The secret weapon for predicting and maintaining this balance is load flow analysis. It's essentially a giant, ridiculously complex mathematical Sudoku puzzle. Engineers use this tool to compute precise steady-state voltage magnitudes, phase angles, and power flows. Assuming we know generation and load, this is exactly how we predict, plan, and stabilize the whole system.
Section 1. The grid's balancing act. Let's visualize the network.
All right, think of this as a bus or a node in the network. It's the physical junction. We're calling it busbar I here, where current is injected or absorbed. Every time transmission lines cross paths, or a generator hooks up to a load, boom, you get a bus. And because power systems deal with known power injections rather than just simple currents, this physical setup spits out some seriously complex, nonlinear algebraic equations we have to solve.
Moving on to Section 2, the 4 key variables. These are basically the rules of the game.
At every single bus in the system, we've got 4 distinct variables at play. You've got real power P, which is your actual working power. Then reactive power Q, which is absolutely crucial for maintaining those voltage levels. Next is voltage magnitude, the strength of the electrical potential. And finally, phase angle, the timing of the voltage wave. But here is the catch, and it's a big one. To solve the system mathematically, we can only have 2 unknowns per bus. That one strict rule literally forces us to categorize every single bus into 3 distinct types.
Section 3. Load buses, or PQ buses, the most common type out there.
Okay, at a load bus, a PQ bus, the net flow of real power and reactive power is fully specified and known. Which makes sense, right? We generally know exactly how much juice a city, a neighborhood, or a big industrial plant is pulling. So that leaves our unknowns. The variables we actually have to crunch the numbers for here are voltage magnitude and phase angle. Now, since these PQ buses make up the vast majority of nodes in any interconnected grid, engineers need a really solid starting point to kick off their calculations. So they use a clever trick called a flat start solution. Since real-world voltages are usually hanging out pretty close to their rated values, they just estimate the initial complex bus voltage right at a baseline of 1.0 per unit, sitting at a perfect 0-degree angle.
Section 4, generator buses, also known as PV buses. Let's talk power generators.
So with our generator buses, the script flips a bit. The active generation, the real power, is known, and the generator's internal controls actively lock the voltage magnitude at a constant specified value. That leaves our reactive power and phase angle as the missing puzzle pieces we've got to uncover during the load flow analysis.
But here is a wildly fascinating nuance about real-world physics. Real generators have strict, hard limits on how much reactive power they can pump out or absorb. If a PV bus just doesn't have the reactive power support to hold that voltage and hits its limit, the math dynamically shifts. We literally just treat it as a PQ bus for that specific iteration. We lock the reactive power at its max limit and calculate the new drifting voltage. It is such a brilliant mathematical adaptation to physical reality.
Section 5. The swing bus. This is a truly unique puzzle piece.
1. There is exactly one of these designated per system network.
Usually tied to the main generator, the swing bus, or slack bus as some call it, has a tightly specified voltage magnitude and phase angle. But take a look at the unknowns here. Its real and reactive power flows are left completely blank. Now, why on earth would we leave the power generation of our most critical plant unspecified in our equations?
It all comes down to system losses.
We simply cannot mathematically know the precise real and reactive power losses across miles of transmission lines and transformers until the very end of the calculation. So the swing bus is strategically left open to physically absorb those discrepancies. It is the mathematical anchor that perfectly balances the final algebraic sum of the entire grid.
Section 6. Solving the power flow. Let's bring all these pieces together.
By locking in our knowns and unknowns across the PQ, PV, and swing buses, we formulate our system equations. But since we know power rather than current, we end up with a massive, gnarly system of complex, nonlinear algebraic equations. You're definitely not solving these on the back of a napkin. You have to unleash iterative computer algorithms. Starting with those flat start estimates, engineers run loops using methods like Gauss-Seidel or the superfast Newton-Raphson method. They just keep updating the values over and over until the power mismatches shrink basically to zero, and the whole grid converges into this perfectly stable, beautiful picture.
It really is an elegant mathematical dance, and it's successfully kept our lights on for decades. But as you finish up this explainer today, I want you to really think about how this delicate equilibrium is shifting. With renewable energy totally changing how we generate power, how is the swing bus going to handle the wild unpredictability of tomorrow's grid? When the power feeding into our puzzle comes from fluctuating wind and solar, keeping this mathematical Sudoku balanced, well, it might just be the greatest engineering challenge of our time.